share. Oops. We had a few questions come up last week that I wanted to answer. It was about the in our moon problem specifically, getting the HP and what HP meant. That was our horizontal parallax. And we're going to use that today when we go to the back and use a table for correction. It's only used on the moon, and it's because the moon is a lot closer to the Earth than all of the stars and the planets and the sun. So that's what horizontal parallax is. And then the V factor, I still have no idea why it's V. I don't know what V stands for, but they call it the V factor. And that takes into account how the cycle of the planets and the moon is slightly different than the sun. Then that's whole, like the lunar day and sidereal day versus the solar day or the standard day. So it has to do with time, basically, and it just takes into account the difference in how the almanac interpolates standard times versus the planet and the moon, how they cycle on a little bit different time. So that's why we have an additional little V factor. So I added that. Other than that, today we are diving into the sextant. So does everybody have a sextant?
Yes.
Do you have it handy?
Yes.
Cool. We will get to know it today. We're going to learn how to read it and how to correct it. Not those other things, but let's dive into it. So what is a sextant and what do we do with it? So it's basically an instrument that has really good precision at measuring the angle between two objects. So the sextant itself is kind of like the point, and then the angle between two objects is going from the sextant itself. So it's just a very precise measurement of measuring the angle between two different points. This little picture indicates different different names of things on the sextant. So we have the arc. So I'll refer to that a lot. So it's the arc is kind of the base. And then you have the index arm, or they call it the index bar. And that's what moves along the arc. And what's attached to this index arm is a mirror. So we call it the index mirror. And that is what we move to reflect off of what we're seeing from the horizon mirror, which is going to be this one. So this one doesn't move. This one's attached to the arc, and this one's attached to the index arm. And then we're going to use some reflection thing that I'll show you in the next slide to make those two the same. But you can see that your horizon one is connected to the arc itself, and then the index one is connected to the index arm, the two pieces that move. So those are kind of like the two basic parts of the sextant. Of course, there's all these little other ones, but so this is a diagram of how it reflects. So we want the two things that we are trying to meet or trying to measure the angle between is a celestial body, example the sun, and the horizon. And that's so we can see what the altitude is and then get that circle of equal altitude as an LOP. So in order to measure those 2 points, we use the index mirror and then the horizon mirror. And then we can see through the telescope. And if we can see both things on the same, in the telescope, then we could see what they measure at the, on the arc. Again, I kind of have the same picture a few different times, but I liked different things about each diagram. So you have object 1 reflected, so it reflects twice. We reflect it from the index mirror to the horizon mirror to your eye. And then the second object is the horizon, and we just see it straight through the horizon. There is no reflection or mirror adjustment on that. So one, you're looking straight out, and the other one has 2 bounces or reflections that it is seeing. This was kind of a more basic version of it, but same kind of thing. Okay, so I'm gonna go back to this one. Well, actually, I kind of like this one better. Sorry. The index mirror, so this is the one that is, the sun is shooting into the index mirror. So you have these slides of different colors. You have blues and reds and greens, and those are going to be, there we go. So we can put them all up so we don't have any reflection. If we put one down, then, so the ones closest to the index arm are helping you see the sun without burning your eyes. The ones next to the horizon arm are the filters to see the horizon, if the horizon itself is really bright and you can't see it. So those filters are for the horizon, and these filters are for the sun or the star, whatever you're looking at. So for the celestial body, those mirrors or filters are closest to the index mirror. For the horizon, those filters are closest to the horizon mirror. And I'll show you this one. Okay, before we dive into it, how to move your sextant. Okay, I'm gonna stop sharing so you can see me. For the horizon filter, it's sometimes the horizon is just so bright that it hurts your eyes and you just want to filter over it. So it just prefers preferences. It just whatever your personal preference is. Which filter do you normally use? So I typically put all of the filters down, and then I'll put one back and see what the difference is and put it down, and put another one back and see what the difference is and put it down. That way I'm not starting with nothing and burning my eyes and then finding which filter works. So I put all the filters in, and then you know, decide. I don't have a typical one that I use. It kind of depends on, you know, the environment that you're in. Maybe the first week you're out there, you're always using, you know, the last one and the first one, and then the, you know, climate changes, the atmosphere changes, and you're using the last 2 or something. So it's really dependent on what the atmosphere is. Okay, good questions. Okay, to move your sextant around. So on your index arm, we have 2 little things that you could pinch together. And that you could move the arm around great distances. You can move it pretty freely if you have these 2 little items pinched together. Then the dial fine tunes it. So this one you can get, you know, the 2 things ballpark together. Once they're ballparked together, then you could fine tune by twisting this dial to fine tune exactly what you're looking to read. I don't have a slide on this. I wish I did.
Bree, quick question.
Yes.
You mentioned there's 4 filters at the top, but what are the other 3 at the bottom? Did you talk about those?
Those are for the horizon.
Oh, okay. I thought the bottom. Okay, so the other 4 include
So
the
the four at the
sun.
top is mainly for the sun. You're probably not going to use a filter for the
I got
sun
it.
or the
Okay,
planet.
thank you.
And the ones on the bottom are for the horizon.
Got it.
So if we look, where am I at? We have a mirror and a glass in this, what your telescope is looking at. Does everyone see that on your sextant? There's just clear glass, and then there's a mirror. So that mirror stays there, but if you are looking straight out at the horizon and the horizon is too bright, you can bring down a filter, just like a little sunglass filter, to make the horizon or the reflections off the water not as bright, so you can see the horizon clearly. Then these go to our index mirror, which moves as we move. And those are the filters for that. So back to these, here, wait, let me bring my PowerPoint up again. Okay, so this is basically what you're gonna see when the two things are meeting. You're gonna see the sun superimposed because it reflected off of a mirror to another mirror and through your telescope, and then you're gonna see the horizon directly out. So through that glass, you see whatever you see out there, which would be the horizon. And then on that mirror, you're gonna see the sun or the star or whatever celestial body you're gonna be observing. For now, I'm just gonna talk about the sun. So when you see those close together, that's when you have a measurement, when they are exactly close together. And what I mean by exactly close together is, I'm gonna do whiteboard, if that works. You share. Oops. Stop share. Stop share. Screen share. Here we go. Okay. So in your horizon glass, this one is a mirror, and this is glass. So this is glass, oops, and this is the mirror. So you will see the horizon on this one, and then you will see the sun or your celestial body on that half. Now, the way it works is this reflection of the sun crosses over to the reflection to the glass side. I feel like I'm saying that wrong, but you will see the sun on both sides of the glass itself. So what you want to happen is, here's your horizon. You want your sun to be right on the horizon. Oops. Barely touching the horizon. So what I swing the sextant. And so what that looks like is you're looking through it with your eye, and then you swing the sextant like this. So you're kind of passing, you're swinging the sextant. What's another word for it? You're twisting, or you're rotating the sextant, but keeping your eye as kind of that pivot point. So
I've heard it also. I think I've heard it as swinging an arc.
swinging an arc. Yes. So
Yeah.
the arc, what you are creating is that arc of the sun. So that the sun, as you are swinging it, is going to go down to the horizon and then back up, and then down to the horizon and then back up. So it creates this little arc of the I got some chats. Rocking, pivoting around your wrist. Yeah. So you want, what the measurement you want is when the sun is just touching the horizon. Now, if it's the star is a lot easier because it's just a little tiny dot on the horizon. So it's so minuscule, you'll be able to see it. So when we are looking at our sextant, we can move it ballpark with these little pinchers, and then we dial it in. So when you have, you know, the sun or the star and the horizon in the frame, meaning in the box, then you start using this dial. Then you start fine tuning and doing the rocking motion or the swinging of the arc, or swing the sextant, whatever you want to call it. Then you use that dial to fine tune as you're doing that little motion there. Does that make sense?
Yes.
Okay. So once we get that measurement, we have to read it off of the sextant. So there's 3 places on the sextant that we will read it. And just like in our latitude and longitude, we use degrees, minutes, and then tenths of a minute. So our standard format. And all 3 of those things are degrees, are seconds, and then tenths of it, it's degrees and minutes. Look at that, I already found a typo. Degrees and minutes, and then tenths of a minute. Hold on, I have to write this down or else I'm gonna forget it. Can't believe I missed that. Okay.
Also, are the numbers backwards? Mine kind of go the other direction. Like 0 is at top. and-
Yes. So you have to figure out what your sextant is reading. So I have some of the standard Coast Guard pictures of them, and then I also have pictures of sextants from my husband's ship and my brother-in-law's ship, and then I have pictures of the sextant that most of us will be using. So we will see a few different readings, and you'll see how different they look. So when you're looking at the degrees, you want, and my suggestion for this is to really ballpark it until you fine tune it. So in this case, I know it's around 30, but probably less than 30, because that arrow is closer to the 0 than 40, or closer to the 20 than the 40. So I think it'll be almost 30, so it's between 29 and 30, but pretty close to 30. So then when I look here, I'm like, okay, so I'm in the higher portion of 29. So 29 would make sense. 29, something high. So here I'm looking at the 0. So this little 0 line, it is at, here's 40, here's 41, here's 42, Here's 43, 44, and 45. So it's between 42 and 43 is where that 0 is. So I know it's somewhere between 42 and 43. Then I find which one of these lines meets up exactly with one of these lines. So that's kind of strange to wrap your head around. But which one of these lines match exactly with this one? In this case, it's R5.
Hey, Bree,
Yes?
I have a sextant got from OCC. I borrowed it. There are no numbers on the blue. It's just, and there's 1, 2, it looks like 6 lines.
Yes.
Is that going to be an issue? Is that
No.
okay? Is that going to be a problem?
No, that is how all of the sextants from OCC are. And so I will show you that one as well. But
All right.
it's the same basic concept.
Thank you.
Okay. So this is another cartoon illustration. So looking at the minute or the degrees, we always start with degrees. We are between 30 and 31 ballpark, right? And then if we look at the minutes, I hate that it says seconds. If we look at the minutes, we are right around 20, where the 0 is. Now that 0 in this little illustration looks like it's 20 even. But it also kind of looks like the 4 is even. I might have called this 20.4. The cartoons are a little bit strange. I'm gonna move on. This is another black and white one. Okay. Same kind of thing, right? We have 30, between 30 and 31. And then where's that 0 meet? Here's 40, 41, 42, 45. I think we already did this one. Okay, here's our OCC sextant. That is what you guys are looking at. The longer line, if you can see, one of those lines on there is a little bit longer than the rest of them. That is your 0 line. So in our case, our 0 line is at the top. And then it goes by 2s. It goes 2, 4, 6, 8, and 1, or 0. So essentially, the 0 line and the 1.0 line should be both meeting if they are exactly in the same. So on your sextant, I want everyone to find 43 degrees, 31.0. So use your sextant, ballpark the 43, and then twist the dial until you can get 31.0. Here's 43. So remember, our marker line is going to be that top line or the longer line. It's just longer by a hair, but it is longer. Okay, so now I'm gonna move your dial. I want to say clockwise or counterclockwise, but I guess that depends on which way you're looking at it. Okay, move your dial so you have, it's just gonna be a little exercise here. So you have 30.5. So you're just gonna move it about, a half of a minute. So you get about 30 point, well, let's do 30.6. So that, so you have the 0 line, and then you have 2, 4, 6. So that 6 line in line with a straight line. So it would essentially be in line with the 33. Oh, let me, I like this clearer picture of it. So you have 40 degrees or 43 degrees, 30 I have 30.6. And then I want you to move it to, let's call it 31.2. What would 31.2 look like? See how as you move the dial, the different lines line up with the other lines of the other dial? Are we seeing that? Okay. This is another sextant with the 0 on the top. So the other sextants had zeros on the bottom. Our sextant has 0 on the top. This was another one with the 0 on the top, but they actually have the 2, 4, 6, 8 on it. But again, you ballpark the degrees, and then you can see, yes, we're between 55 and 56. If my 0 is here, it's between 39 and 40, but pretty close to 39. And maybe my 8 lines up, but I know it wouldn't be on the 8. And it kind of lines up with the 10. So I called it 39.1. Just because you can see where the 39 is and that the 0 is so close to it. If it was 39.8, that little 0 mark would be closer to the 40. So use that as a guide of figuring out the weird little lines. Is where is that? I know it's really small, but where is that 0 line in reference to the next line? Okay. Okay, this is an example of our sextant. So we have 71, 2. So this could be, you know, 71 and something or 72 and something. I don't really know from just this looking at this part. Then when I look here, I have all low numbers next to my 0. So I know that it would be 72 point something. So I am past that 72 mark. And so I would have 72.04, and then I have to figure out what my tenths are. So I'm kind of right in between, but where are my lineups? I have 2, 4. So I'm going to say that 6 and that 4 line are closest to even. So that would be 04.4. Okay. Now this is the quiz. What do you guys read on this one? Throw some things out there. I'll write it on the whiteboard.
Should we shout it out?
Yeah.
2942.8.
42.8. Does anyone come up with something different? All right, we got 2942.8. All right, let's try this one.
$30.
This one has a strange little dial thing here, but
29.4.
29.4. I said that it's about 29.4, that 0 was on that side of it, and my 8's lined up. So I said 3.8. But the reason I want you to adjust it is so you get familiar with how different things look on your sextant that you're reading. So try to get familiar with, like on yours, try to get to 29. Let's try to get it 2903.8.
So Bree, just to level set here, I'm just trying to figure out if we need to get better glasses, but I mean, we're talking tenths of an arc minute now, right?
Yes.
Okay, so that's tenths of a nautical mile, right? Okay, so I'm not gonna freak out if I'm at,
You don't need to.
0.7 versus 0.8 until I'm a
Your
lot better with
pencil
it.
lead will be a tenth.
Okay,
Right?
okay. I just want to kind of level set.
So, but at the same time, all of those things add up, right?
Yep.
Like if we have a tenth here and 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 a tenth here, we can be off. I mean, you're not going to be super far off because most of the time our celestial is middle of the ocean navigation. Because if you were actually at, risk of colliding with the shore, you'd be using coastal navigation.
Right. Okay.
So yes, our, we need to know.
Roger that, Ted. Yeah.
Yeah.
Okay, thanks.
Okay, so does anyone have any more questions about the sextant itself?
Yeah, it looks like the one that I got, you can't even read tenths of seconds on it. So.
Okay, so all you're reading is minutes?
Yeah, degrees and minutes, no tenth. Yeah, no.
Okay.
Yeah, well, I guess that's close enough.
Yeah.
I mean, did you just rent that, or how does that work with the school as far as getting the kind of sextant that you have?
Janice, do you want to take that one?
Sure. If you need a sextant for the class, we have several of the Davis sextants. We have MK15s and MK25s. And the people who've rented, I provided them with MK25s. You can rent it for the duration of the class for $50.
Okay.
And if you need a sextant, please call the office and let us know. We're not shipping them because we're afraid that postal or UPS, whatever, they're a little rough with packages. So
Hey, Janice,
you would need to come by. Yeah.
just a clarification on that. Maybe I made a mistake. We're not actually renting it for $50. We gave a deposit for $50
Yeah.
and we get $50
Yeah,
back.
that's right. I'm sorry. You're right.
That's a big
It is
difference.
A deposit. You're borrowing it, and the deposit is $50.
I just didn't want to scare anybody with that $50 rental fee.
Yeah.
And
Thanks, Frank.
and there are plenty available. So
Janice, my understanding is the difference between the 15 and the 25 is the 15 has a lighted arc. That's the only difference.
yeah, and the thing is the 25s, I don't believe there are batteries in them because I did not know when they would get used again. So I didn't want batteries going bad inside of them. So to the people who've borrowed, we can take a look and see if the light will work. And if not, we can, it'll take a battery for sure, but if the light doesn't work, I can swap them for ones that might have better working lights.
Double A's or triple A's?
I'm trying to remember. It's a tiny light.
Doesn't matter.
Yeah, it's
Yeah.
going to be a little battery. And I did clean them. They hadn't been cleaned in a long time. And I cleaned them and went through them and looked for problems. And the one thing I did have to replace mirrors on a few, and I was not able to adjust the mirrors simply because I was having some trouble with my eyes at the time, and I couldn't see well enough to do the adjustments. But we'll be going through those adjustments anyway, I think. So.
Hey, Bree, two questions before we move on.
Yeah.
When to use, tell us, specific to the Mark 15 or the 25, when would you use the telescope versus not? And when you do not,
When would I use the light?
no,
Light.
the telescope. There's a telescope. There's two different sighting methods with the 15. There's a telescope, and then there's just a round tube.
Oh, okay, yeah. Yeah, I'm gonna let Bree answer that because I think it depends on the type of work you're doing.
I would say with the telescoping one, it would make the star bigger, but it would also, I like to use just the basic one because if the star is bigger, it also makes it harder to find that star because you have to find it within the little square and then bring it down. But so it's kind of that like catch-22. You'd get a more accurate reading if with the telescoping one compared the horizon to the star. But with the telescoping one, it would be, you have to be very accurate in finding the correct star and keeping it in the horizon glass as you bring it down to the horizon. So
and the follow-up there with the tube that doesn't have the magnification, there's a kind of a cutout, and I was wondering what that's for. Is that kind of a shade? So you put the cutout on the bottom, or what's the proper use for that cutout there?
I would say just depending on the brightness of your of the day, like it would go more on the side of your face.
Oh, the piece in your your left hand is not what goes on your eye?
This is what would go on your eye.
Right, but then
or this one.
Well, there's a piece that fits into the piece on your in your right hand.
Okay, let me get
It looks like an eye cup.
Yes. Oh, that doesn't really.
Yeah, there you go. So it fits into the end that you were just holding with the cutout.
Fits into this end.
What's that?
Okay.
Yeah. So I was wondering what the correct position for that cutout should be after you put it in after you mount it. Is that like a shade and therefore you put the cutout on the bottom, or I'm not really sure.
That might help with glare. You know, if you're getting a little bit of light from the side and it's kind of interfering with what you're trying to look at through the sextant, it might kind of protect that.
I don't think I'd want to look at it either way.
Huh.
I've always just used the basic, but I guess you could put it on there like that. It kind of makes the tunnel, oops, of what you are seeing kind of protected from glare.
Right.
But you don't get like you're looking directly at the glass. I mean, here you're not looking you do have two little plexiglass things that you do look through with that setup.
It's a telescope, right?
Yeah. So
if I'm understanding correctly, the cutout should be on the bottom, so the long side is shading the your eyepiece there.
yes, so you're still going to look at the wide cut.
Right.
That's where your eye goes. And then the little slotted piece would, depending on where the glare is coming from, I would say, you know, on the outer side or the upper outer side.
Got it.
Yeah. Okay, so another thing I wanted to show you with the sextant is how we use it. So typically, this is how I do it, and everyone can do it differently, whatever works best for you, but this is my strategy. To find the sun, I set it to ballpark 0. So when I look through my my glass, I should be seeing whatever is in front of me on both sides, because it's at ballpark 0 that my angle between the two things are at 0. So I would find the sun with all of my, you know, shades down, so I'm not burning my eyes. I find the sun, so the sun is in my square. And then I hold my two little pinchers together, and I do, keeping the sun in the square, I do this kind of parallel thing where I call it bringing the sun to the horizon. So you start moving, keeping the sun in the square, so your index arm is not moving, right? So if I show you again, my index arm is staying vertical. My index arm is not moving. What's moving is my right wrist, and I'm moving the arc, which is this part. So I pinch the two, I keep my index arm vertical, and then I move my arc to measure the sun until it's at the horizon. Maybe it's there. Did you guys see that? And then once it's
Yeah,
there,
do it again,
Yep.
Bree, as if you're looking through it and moving the arc, because you're rocking your eyepiece back and forth. Is that what you're supposed to do?
okay, so I'd set it to 0 so that my sun my sun is in the square. And you could like move it around, find that the sun stays on both sides of the square, and then you pinch this, and then you bring the sun, so you want to keep the sun in the square the whole time until you see the horizon, and then you do the little rocking, swinging the arc, and dial it in until you get what you want. Is that better?
So, yeah, when you see it then and you do the rocking, it's at the exact point that the sun touches
Correct.
the horizon.
Correct.
Right there.
Correct.
Got it. Perfect.
Yep, so that sun will go up and down. It's creating that arc, and right as it touches, so when you're looking at the sun, you might end up having to look this way to get that arc going. Like maybe you're not looking the right way. So
Right.
you're finding that, you know, smallest possible distance, that smallest bearing, which then we're going to calculate.
Perfect.
The
Thanks.
tracking is to make sure you get a perpendicular sextant, because when it's perpendicular, it's when it's the lowest.
Yeah. Okay, so that's what I do for the sun. For the star, keeping that little tiny star in the box is a little bit harder for me. So I do my pre-planning, so I know what stars I want to shoot and relatively where they're going to be. So if I know my star is going to be about 45 degrees, I'll put my sextant to 45 degrees, and then I'll look at the horizon and kind of do this like, where's a big bold star with lots of magnitude? Oh, there it is. And then I'll fine tune it until it's at the horizon. So that's how I do it. Some people can find the star and then bring it to the horizon, but sometimes I feel like most of the time when you're not looking at it directly, bearing wise, when you bring it down, you just lose it So then you can like try this way, but you just lose it. To me, it's harder, but try both ways out, see what works. Some people prefer that way, setting it to approximately what you think the sun is going to be at and finding the sun. That they don't like doing the two-handed, I don't know what you call this, the glide or something. So it really just depends on your preference. So try both out, and we can work with that on our practical day.
Bree, quick question. When you do the pre-planning, and this might be premature here, but the number that you're looking for in terms of the direction around the horizon, that's the LHA, is that correct?
No.
No.
The ZN, the azimuth.
The ZN, okay.
ZN is what we're looking for, the bearing. So
Right.
I know when we're not on a vessel, we won't have, you know, a compass to look at or anything, but you can, I have it in my homework, you can look at it, where you can, I typically would either draw the ship. In this case, we're going to be on the pier, so I just drew the pier. And you can use that as a reference, like the boat is headed this way. So the first star I'm seeing is going to be, you know, fine to starboard. The second star I'm shooting is going to be on the starboard beam. So you have that relative thing that you're looking at, because you're probably not doing it right on top of a compass.
Oh yeah, I'm just talking about the pre-planning to get you in the ballpark.
That would be your altitude and your, so your HC and your ZN.
Got it.
Cool. Okay, so that was the sextant itself. Now we're going to dive back into the nautical almanac. So what we get from the sextant, we call HS, which is that raw sextant altitude. So let me bring this back up here. Okay. So, kind of a little bit of review from last week, going back to what we need. This is our site reduction form. We needed our assumed longitude and assumed latitude. That's our assumed position. And then we need our intercept and our azimuth to plot. So what that intercept is, the difference between the calculated altitude and the observed altitude. But we haven't quite gotten to the observed altitude yet. So kind of review here. We have our assumed position and then the intercept and the azimuth, and that's how we create a line of position. So our assumed position takes into account our LHA. That's why we need our LHA, very important. And then the azimuth is the ZN. And then the intercept is that observed altitude versus computed altitude. So that's where our sextant altitude comes in, is we change it into what we call an intercept. I don't know why it's called an intercept. It's called intercept, and then the abbreviation for it is a little a. Both of those things don't make, I don't know why, but that's what it is. Okay, so our whole site reduction form. We had the navigator's info. We had the nautical almanac. Last week we did the first half of the nautical almanac. This week we're going into the bottom half of the nautical almanac portion. So the two things that we note when we are out shooting is the time and the HS. So that's that raw, that HS is our raw sextant altitude. So whatever that sextant is reading is HS. And then we apply all of these corrections in order to get HO. And then we compare our HO to our HC. Let's bring it back to this one. Our HO and our HC, and that's where we get our intercept. So that's how we can calculate our line of position. So it's one more step here. So we're going to go through what these corrections are and how we find them. And they're in the Nautical Almanac. Make sense so far? Cool. Okay. So we have 3 different types of altitude that we will talk about. We have HS, HA, and HO. HS is our sextant, HA is our apparent altitude, and then we have our observed altitude. So our final, all the way corrected, is what we have as our HO. The HS, we have corrections for errors on the sextant itself. And then from HO to HA to HO, we have corrections for errors in the atmosphere. Does that make sense? So there's errors for the sextant, and then there's errors for everything in the atmosphere, whether it's refraction, dip, pressure, all those different things. Actually, dip we use on this in the sextant part, but okay. So first one, we have HS to HA. So this little thing that I'm referring to, I thought it was in there, but stop sharing real quick. On your Google, oh, I didn't have it over here. Okay, on the Google Classroom, under Breeze Quick References, we have the sextant altitude corrections. So this is, you have a little bit different for each kind of celestial body that you're looking at. So I have one for the sun and the stars, one for the planets, and one for the moon. So we're going to be talking about the sun just as a basic one in this lecture. But just keep in mind that it could be a little bit different for the celestial body. And we are going to do an example of all of them. But I just wanted to keep that in the back of your head. Okay. So, and that's what I'm referring to when it's just part of the site reduction form. So from HS to HA, we have 3 corrections that we're going to talk about. We have the instrument error, we have the index error, and then we have correction for height of eye, and that's called dip. I think I go here, yes. The instrument error is found on, it's from the manufacturer. So it's usually on a instrument error card. These are some examples, but maybe Janice knows, was there any instrument error cards? And Bill said he didn't have one on the new one that he got. So maybe the plastic sextants don't have them.
No, the Davis ones don't have
Most
them.
of the sextants that OCC has, the Davis instruments, do not have instrument error card.
We can't hear you, Janice.
I'm sorry.
That's
Most
better,
of the
thank you.
sextants that I've gone through that OCC has do not have inspection certificates.
Okay.
So they don't have error cards.
Okay.
There are methods that you can use to check the alignment of the mirrors, and so adjustments that you can
we're
make
going to
to
go
the
into that
mirrors.
one on index error.
But like this non-adjustable error that they're mentioning here for the Tamaya, the Davis doesn't have that kind of information.
Okay.
Yeah.
On sextants that I've used on ships, they do have it, and it's usually this instrument is free of errors for practical use. So typically it's always 0. I've never actually seen it with an error, but it's possible. And yeah, maybe the Davis
Yeah,
one just
But
don't-
like I said, on some of the Davis instruments, the Davis sextants, some of them needed new mirrors. And so I put the new mirrors in, but I was trying to adjust them, which would be probably your index error correction. But I don't know if I did a very good job. That would have to be checked before you actually tried to use it.
well,
But it's basically just making, you just adjust the little screws. So,
okay. So instrument error is from the manufacturer and it's typically 0. The next one is our index error. So our index error, in my mind, kind of boils in all of your other errors and sets it to 0. So we find our index error before every time we shoot. So if we're shooting sun lines at 11, we find our index error. If we're shooting sun lines at noon, we find our index error first. If we're finding our sun line at 1300, find the index error. If you're doing stars, find the index error at the beginning, and then you don't need to do it for every other star. Just do it at the beginning of each time you are taking a reading. If there's like an hour in between, you can do it in between.
So that's just like you're just manually cranking that?
So what you do, you could try it right now. It works better if you have something far away from you.
Okay.
And something flat. So I'm looking at the house out the window right now.
Yeah.
So it's ballpark 0. I'm looking at the house out the window right now, and you can see it uneven on your mirror. Or you could look at something across the room, but the further away it is, the more accurate. So what we'll use is the horizon itself, because I know the horizon is a straight line. And then you swing back and forth until your two things stay in line. There. I'm gonna call that. So I have, mine right now is about 21 degrees off the arc, but I'll tell you about that. So mine's about 21 degrees off.
Okay.
But different things you can bump the telescope, you can bump the index arm. A lot of times with the metal sextants, they're in a, AC bridge that's nice and cool, and then you bring it outdoors and where it's hot, and it can fog up, it can change, the metals a little bit. There's just lots of different things that the index error kind of bundles together, and it sets everything at a 0. So for this exact moment, when I am going to be using my sextant, this is my 0. That's what you're coming down to, that my index arm and the horizon, this is my 0 point. It's most likely not going to be the 0 point on the sextant itself. You're kind of creating that 0 point or that baseline that you are going to be measuring from. Does that make sense?
Yeah.
Okay. So, so how you do it is you look at something far away that's a straight line, typically the horizon, and you want it to be 0. So you're creating that 0. And how we read it is either on the arc or off the arc. So that's saying, is it on, as in it's closer, it's on as in it's 0 plus, or is it off as if it's in the negatives? And that's why, you have this negatives way out here on your sextant.
Okay.
I mean, there's way more than you need, but so in reading this, this one right here, our 0 line, here is the 0 that, that the sextant says, and the 0 that I've created is up here.
Okay.
So how many minutes is this? So I'm going to say this is off the arc, right? It's not in the plus side, it's in the negative side. So I'll click it. So it's 6 minutes off the arc. So I'm reading 54, but from 0, I have 1, 2, 3, 4, 5, 6. So I have 6 minutes off the arc.
Yeah.
Does that make sense? So if it's, I like to say, if it's off, you put it on. If it's on, you take it off. So it's a plus or minus that we have to decide, are we adding or subtracting this from our raw sextant altitude? So if it's off, you need to subtract 6 minutes to get a more accurate one. This is a correction. In this case, we have one on the arc. We have 0 here, and then it's on the plus side. So we have 4 minutes on the arc. So in order to get an accurate reading, I would subtract those 4 minutes because this is my baseline. This is my 0.
Okay.
Okay. Any big questions on your index error? Okay. 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 The last one in our sextant error is dip. And this is what our height of eye is. So if you are on, you know, a tall ship or a kayak, your height of eye is going to be different, meaning your horizon is going to be different. So this kind of goes back to like geographic range that we've talked about in coastal navigation. We need to take account for that in our celestial navigation and where that horizon is. What am I looking at this point to where the star is this point? So in the very first page of your nautical almanac or on your bookmark is your dip calculation. So your dip has whatever your height of eye is, and then it has the correction. So your height of eye in meters or in feet, and then it has the correction. So when you are making an observation with the sextant, you need to have an approximate, what is my height of eye? Am I 20 feet? If I'm on the pier, am I going to be like 60 feet above the water line? What is my height of eye? So yes.
So it seems like if you're on a pier, a stationary object, it would stay that
Yes, you're not going to be changing.
would stay constant. Where if you were on a boat going up and down with the tide, or would it be variable with both?
It wouldn't be variable on the boat.
Okay.
The things that would make it variable on the boat is if your draft changed.
Okay.
So,
Or you move to a different spot on the boat that's higher or lower.
yes, or if you move to a different spot on the boat. And my height of eye is going to be different than your height of eye. I'm only 5 foot. You might be taller, most likely. So, I mean, but again, this correction, what do we have here? For your height of eye, give or take 1 foot is the same correction. So you can ballpark it a little bit, but again, all those little tenths here, tenths here, tenths there can add up.
So Bree,
Yeah.
quick question.
Yeah.
I'm standing on a moving boat in swales of 4 to 5 feet,
Mm-hmm.
and my dip is going to matter by 1 foot.
No.
Yeah. How do I judge these minute corrections, which when you look at them over a long distance matter, but in the reality, I'm standing on top of a deck that's moving up and down,
Yes.
trying to take a shot.
Yes. I would say how I would calculate, like, a lot of times it'll say on something, but you can look at, the measurements from your, keel of your boat, how high is the bridge, or how high is the wheelhouse, or if you're on the flying deck because you're shooting the stars, how high is that above the keel, and then what is your draft? And yes, there's going to be swells and things changing that, but ballpark from wherever you are, like if you're on the flying bridge or you're on the back deck or wherever, minus your draft, use that number.
So to echo Tim's question, I guess if we're at the dock, you'd measure the water line to the likely position, say next to the mast you're going to use to take your sight up to your eye.
Correct.
And then, I mean, if you're going to Hawaii and you're in 10, 15 foot swells, you're just going to have to average the swell height or try and figure out if you're in a dip or if you're in a trough or a crest or what have you.
Correct.
Okay.
Yeah. Okay.
Bree, my recollection is that it sounds like it's more difficult than it really is to take a sight on a boat that's moving up and down. My recollection is that the angle really doesn't change that much. So, as long as you got a good average, you don't really have to get it down to the foot in terms of the dip correction.
Because it's so far away on the horizon.
Right.
So, ballpark as best you can, and go with that. Okay. Hold on a second. Okay, so that was dip. Oh, okay, and we always subtract our dip. It does give us that little negative sign there, but we do always subtract it. Okay, then we get our, so then that's our apparent altitude. Then we're gonna move into our horizon or atmosphere corrections. So that's where we have our refraction, or I like to call them just the refraction corrections, our A2, 3, and 4. So in this picture, you can see this C is our visible horizon. And this is the circle, the inner circle here is Earth. And this is the center of Earth. And directly out from the center of Earth is our celestial horizon. So the celestial horizon is just cutting the Earth in half from our zenith. So it's different from a celestial equator, right? So it's perpendicular from our zenith to our celestial horizon. Those are perpendicular. We have our zenith and our nadir and our celestial horizon. So we are a little bit out, right? We are on the Earth's surface. So we need to take into account some differences. So our visible horizon can bend because of the atmosphere. And then we can also have our geometrical horizon. And then we have our celestial horizon, which is what we want to bring the body to. Your sensible horizon is from you directly out. So that we don't use for anything. Okay, so this is our portion of going from HA to HO. So this is that apparent altitude to our observed altitude. looking for things in the atmosphere. So let's find, and this is where we get real into the Nautical Almanac again. So open your almanac to the beginning, the first couple pages. And the first one you'll see is A2, altitude corrections for 10 to 90 degrees for your sun, stars, and planets. And then there's an additional correction for Venus and Mars. But you have your apparent altitude, which is your HA that you go in with, and then you get your A2 correction, your refraction correction. So that's on the first page. If you are in low, if you observe the sun when it's really low, like almost setting or just rising, then you use A3. So this is for if your altitude is between 0 and 10. So typically we will not be using this one. We'll be using A2. And then if you want to get super accurate, you turn the page to your A4 correction, and that can take into account your temperature and your pressure and how your line of sight can bend your horizon or make your horizon a little bit different. And then the last one we have is our horizontal parallax. I think I said that right. And that is going to be in the back. So many ads. Geez Louise. You have your moon corrections, or your moon, your HP correction, because the moon is so close to the Earth. We have our horizontal parallax right here. Again, we go in with our apparent altitude, our HA. HA is apparent altitude.
So that last one was on page 34, or Roman numeral 34, I should say. The moon corrections.
Roman numeral 34, yes.
Okay. And that doesn't have a correction letter like the other guys do.
So this little one is for the sun. We'll put HP for moon.
Got it.
So if I bring this one back up, our moon had HP.
Got it. And one other question, Bree. I know DIP is applicable to the measurements, no matter whether they're 0 to 10 or 10 to 90. How about the stars and planets? Do they, excuse me, are they applicable? Or the ones in the middle there on A2, are they applicable to all sites or just the 10 to 90 sites?
Sun versus stars and planets?
Yes.
You have to find it on either A1 or A2 or A3. So on your A3, the middle section is sun, whether it's October to March or April to September. And then the last column is for your stars and planets. I think I have, okay, I go into it. I was like, I think I have it. Okay, so A2, we go in with our apparent altitude. And did you observe the lower limb or the upper limb of the sun? Maybe the lower limb is covered by clouds and we had to get the upper limb. Typically we'll get the lower limb because it's easier to see, but maybe for some reason you couldn't and you got the upper limb. But I like on the bottom here, it always says apparent altitude, because you go in with your apparent altitude, equals your sextant altitude corrections for index error and dip. And that's because instrument error is always 0. They didn't put that in there.
So I'm not sure that answered the question. So
yes,
you have two tables for the sun, stars, and planets, correct? You have the A2 and A3.
Yes.
And so, but dip is, you use dip well, no matter which one you use, correct? A dip is applied no matter which table you use.
Correct.
And my question is, in the sun and the star and planets correction, is that applicable to no matter which side you use, or is it just 10 to 90?
It is applicable for whatever your altitude correction is. You have to apply either A2 or A3 to all sun, moon, and stars. So here on the A3 section, if you have a low sight, you have the sun corrections here. So we go in with our apparent altitude. It's between 0 and 10, right? We have 0 to 330 and then 330 to 10. So we go in with our apparent altitude. Let's say I think it's.
Now, I understand all that, Bree. My question is, on the other side, the middle column, is that just applicable to 10 to 90 degrees, or is it applicable to both sides? The stars and planets section. Is it applicable to 10 to 90 only, or is it applicable to 0 to 10 as well?
10 to 90 only.
Okay.
If your other one, you use this one, stars and planets.
I understand. But you look at the dip is applicable to both, correct?
Correct.
Okay. So that was why I was asked that question.
Okay. Yes. I get what you're saying now. Dip is different. It shouldn't be under that title, I guess is what I'm saying. I get what your question is now. Okay. Are you good?
I'm good. Thank you.
Okay. So we have our A2. We go in with our apparent altitude and we get our correction. For the A4 with our temperature and pressure, we go in. Do I have another thing? No. Okay. So we go in with whatever our temperature is in Fahrenheit. So let's say we're at 70 degrees Fahrenheit. And our pressure. What should we say our pressure is? 170. So we'll say something around here, where we meet the 270 and 1,000. So I'm going to be in the J column. Is that what that puts me in? And then I follow the J down here and see what my apparent altitude was and what my J, and get my correction. We will do an example of this, but that's basically how you use this graph. You meet these two wherever they are, and then you follow what column you're in, or diagonal thing. Okay. Okay, and then we have our moon correction, which isn't on here, but for the moon, we have the moon correction, the HP correction. We go in with our apparent altitude, and here our apparent altitude is broken up a little bit. So we have 0 to 35, and then on the next page, we have the 35 to 70, I think. 35 to 90, excuse me. So this page is our 0 to 35. This page is our 35 to 90. So you go in with what you think your apparent altitude is, and then, oops, shoot, I wanted to scroll down. This is where we have our upper limb and lower limb. Upper U and L is for the upper or lower. And so then we find our, oh, HP was what we got from our daily pages. So then you go in and you find what your correction is. And then I always say, whenever you're doing the moon, read the instructions for the correction table here, because it will remind you, and I can't even remember off the top of my head, if you observe the upper limb, you add 30 minutes to it. Automatic add 30 minutes if you are observing the upper limb. So always refresh that one if you are doing a moon site. Okay. I mean subtract, not add. Okay, I said subtract. So we have our sun and our stars. We have our planets. And remember, we have that additional correction if we have Mars and Venus. And then for the moon, we have that HP correction and add if it's on the, or subtract, I keep saying add, subtract if it's on the upper limb. But it does explain that in that little table because obviously I forget what to do. So we went from HS to HA to HO, and we need that HO to get our intercept.
One quick question on A4. It says you're supposed to, after you get the letter, the correction letter, you're supposed to use the apparent altitude, that's HA.
Mm-hmm.
So is that with or without the A2 and A3 correction?
Without.
Okay.
So it's HA is just index error and dip.
Got it.
Okay. So that little form that we just went over is in our site reduction form. We had HS, index error, dip, HA, A2 or 3, and then our HO. So this is where we're at in our site reduction form. Did it again. Okay. So let's do an example. Are you guys ready? I might go back and forth between the camera and the screen. So we have on July 31st, 2020, we have a DR position and we take a site of the sun, excuse me, with a chronometer time with a chronometer error. So in this case, we don't need to know what our position is or what our GMT is. All we're doing right now is seeing what our sextant, getting our sextant corrections. We did make a note that our index error, so we did this before we shot, was 15.2 minutes on the arc, and our height of eye is 50 feet. What is our HO? So for HS, we put in that raw sextant altitude that we got. That's our HS. And then I need to calculate what my index error, or I can plug in my index error. It was 15.2 on the arc, so I need to take it off. So I'm subtracting it because my 0 is going to be past the 0 on the sextant. My 0 at that moment. So that's index error. And then dip, we use the dip table. So everyone find your dip table. And our height of eye is 50 feet. So we are in between the 49 and the 51. And we got a height of eye as 6.9. Did everyone find that dip?
Well, the height of I is 50 feet, but the correction is
Dip.
6.9.
Yeah, dip is 6.9. So now that we have our index error and our dip, we can calculate our apparent altitude. So we calculate apparent altitude. So I typically use the calculator so I don't make a mistake. But who knows? There's lots of typos in these PowerPoints. So we subtracted our two amounts and we got our apparent altitude. Now we could go in and use our apparent altitude to get our A2. So our A2, we observed the sun in July. So that is going to be the April to September section of our A2 column. So we have the sun in September, or April to September, because it's in July, and then we go in with our apparent altitude. So our apparent altitude was 46 degrees, 40 minutes. So we have the 40 and 29 and the 48, 52. So a wide spread here. So our 46 degrees, our A2 correction would be a plus 15.1 because it was the lower limb. I think I said that. Yes, it said you took a sight of the sun's lower limb. So we have a correction of plus 15.1. We put that in our A2, and then we can calculate our HO. How did you guys do on following along that?
Good.
Good? Okay. Making sense so far? Okay, well now we're gonna practice. Well, let's take a breather first. Perfect, 8 o'clock. Let's come back at 8:10 and we're gonna start on the homework. All right?